Hello students, welcome to the student brand. Now we are going to discuss about current electricity. So let's start. Hello students, welcome to the class. This is your sir. Today topic is current electricity. Current electricity is nothing but the rate of flow of charge. So I equal to Q by T. I equal to Q by T. The rate of flow of net charge, the rate of flow of net charge through a cross-sectional area is called electric current. I equal to Q by T. I equal to Q by T. Yes or no? I equal to Q by T. SI unit of current is ampere. SI unit of charge is coulomb. Yes. So instantaneous current, that is I equal to dq by dt. I equal to dq by dt. This is average current. Average current, and coming to this one is instantaneous current. Current at particular instant. Instantaneous current. Okay. So once again, SI unit of current is ampere. SI unit of charge is coulomb. The rate of flow of net charge, the rate of flow of net charge through a cross-sectional area is called electric current. I equal to Q by T. So I equal to dq by dt is the instantaneous current. Instantaneous current. Understood or not? So I hope it is very clear. SI unit of current is ampere. SI unit of current is ampere. SI unit of charge is coulomb. SI unit of time is second. So 1 ampere is defined as 1 coulomb of charge flowing through unit cross-sectional area per second. 1 ampere is defined as 1 coulomb of charge flowing through unit cross-sectional area per second. Okay. So now you can see this is the conductor. This is the conductor. So will you say only 1 electron flows, current is flowing? Will you say only 2 electrons flows, current is flowing? Will you say only 3 electrons flows, current is flowing? Will you say only 4 electrons flows, current is flowing in the conductor? No, we can't say like that, right? Number of charges are moving in the conductor. Number of charges are moving in the conductor, then only we can say current is flowing. Then only we can say current is flowing. Yes or no? So E positive, E negative, E positive, E negative, E positive, E negative. So charge is quantized. Charge is quantized. Q equal to plus or minus Ne. Q equal to plus or minus Ne. Okay. On 1 electron, 1.6 into 10 power minus 19 coulomb. In 1 coulomb, 1 by 1.6 into 10 power minus 19. Then you will get 1 by 1.6 into 10 power 19. Then you will get, so if you do it, 0.625 into 10 power 19, that is 1 coulomb. So if you are getting 1 coulomb, 6.25 into 10 power 18 electrons are present. In 1 coulomb, 6.25 into 10 power 18 electrons are present. So you have to remember these points. Understood or not? You have to remember those points. On 1 electron, 1.6 into 10 power minus 19 coulomb. In 1 coulomb, 6.25 into 10 power 18 electrons are present. Okay. So I equal to dq, I equal to q by t. I equal to dq by dt. So SI unit of current is ampere. SI unit of charge is coulomb. SI unit of time is second. Yes or no? So I hope it is very clear. So these are the points. These are the points. And one more point. So the flow of charge can be obtained. First point is So the flow of charge can be obtained by multiplying constant current with the time interval. The flow of charge can be obtained by multiplying constant with current. Okay, so constant current and change in interval. So the flow of charge can be obtained if the current is the function of time. If the current is the function of time, the flow of charge can be obtained integral t initial t final. Okay, so I dt. Then third one, the flow of charge can be obtained by area under the IT graph. Area under the IT graph. Okay, so I on y axis, t on y axis, I on y axis, t on x axis. Then we can see here. Understood or not? So I hope it is very clear. So just check once. Next, we'll discuss about based on magnitude. Current can be divided into two parts. So based on magnitude, current can be divided into two types. One is direct current, another one is alternative current. One is direct current. Okay, so here you can see based on magnitude and direction. So one is DC, second one is AC. So if both magnitude and direction does not change with respect to time, both magnitude and direction does not change with respect to time, both magnitude and direction of current, okay, does not change with respect to time, that is called DC. If both magnitude and direction changes with respect to time, that is called AC. So DC example, cell battery, and DC dynamo. Coming to AC, so AC dynamo, okay. If the charge is flowing in a circular path, if the charge is moving in a circular path with a frequency f, okay, so I equal to Q into F. Understood or not? So I hope it is very clear. Next, so next we will discuss about drift velocity and relaxation time. So if the concept is clear, just click on like button. So let me know the concept is clear. So if you understood the concept each and every time, so topic, just give a thumb, give a like button. So drift velocity Vd and relaxation time. Tau. Okay, so drift velocity. What is the drift velocity? So when electrons are moving in a conductor, experience some force. Yes or no? When electrons are moving in a conductor, experience force. So it will produce acceleration. So when electrons are moving in the conductor, it experience force. It produce acceleration. Right? Yes. So here I am taking this current. Current is flowing like this. So electrons are moving in this direction. Okay. So that is a drift velocity. So the force F equal to F equal to QE, F equal to QE or EE, F equal to QE or E. So F equal to MA, F equal to MA. So MA equal to QE equal to EE. Then A equal to QE by M. Then EE by M. Okay. So coming to the drift velocity. Coming to drift velocity. Drift velocity is nothing but, so in the conductor, suppose you can take this the conductor, electrons are moving in the conductor. So one electron is moving with some velocity. Okay, so normally when we are moving in a single path, so people are there around us. Okay, so we are moving to some speed or some velocity, but we move in particular direction. So many are there moving around us. Then what happens? So we will hit, right, like that. So here also electrons are moving in a closed conductor. In a closed conductor, then automatically this electron is going to hit another electron. That electron is going to hit another electron. So initially the velocity, the electron has particular velocity. After collision, the velocity may change. So for the second electron, velocity increases. The first electron velocity may decreases. Okay, so it depends. Understood, Anna? So that time, the overall, if you consider the overall, the average constant velocity of an electron moving in a conductor is called drift velocity. Average constant velocity of an electron moving in a conductor is called drift velocity. And coming to the relaxation time, as I mentioned, when electron is moving in a conductor, one electron will hit another electron. That electron will hit another electron. Here you see, this electron is going to hit this electron is going to this electron. So then keep on collision is taking place. So collisions will take place. Definitely collisions will take place because electrons are moving in a closed conductor. This is going to hit this one. This is going to hit this one. This is going to hit this one. So keep on bombardment, keep on collisions will take place. That's true. But so between one collision to another collision, there is a time gap. Yes or no? So time gap will be there. The average time between two successive collisions is known as relaxation time. The average time between two successive collisions is known as relaxation time. Yes or no? So I hope it is very clear. Understood? So coming to the next one. Current and drift velocity. Current and drift velocity. Current and drift velocity. Current and drift velocity. Current I, drift velocity. Drift velocity Vd. Okay, so this the conductor. For conductor, area of the cross section is there, right? Okay, so here now I am taking this area of the cross section A. So and until here I am taking this is L, length of the conductor. So anyway, displacement, distance. So electrons are moving here inside of the conductor. Current is moving in this direction. Electrons are moving opposite to the movement of the current, or current direction, opposite to current direction. Electrons are moving. So V equal to L by T. From this, L equal to V into dt. Okay, velocity equal to displacement by time taken. Displacement is nothing but, so we are taking here, that is L only, L equal to V into T. Now L equal to Vd into delta T. So that is nothing but Vd into delta T. Understood or not? So now volume. What is the volume formula? Volume equal to length into area of the cross section. Length equal to Vd into delta T into A. Okay. So now number of electrons present in the particular volume. So N is the electron density, free electron density we can say. Electron density, free electron density. Okay. So now you can see number of electrons present in the particular volume. Number of electrons present in the particular volume, that is Vd into delta T into A into N. Okay. So now we know the flow of charge. N, A, Vd, delta T into E. Yes or no? Flow of charge. Now current I equal to delta Q by delta T. That is N, E, A, Vd, delta T by delta T. So delta T, delta get cancelled. So what is the current? So I equal to N, E, A, Vd. Understood or not? Now current density formula. What is the current density? Current density J equal to I by A. So J equal to I equal to how much? So I by A, I am writing once again. N E A V D by A. So A get cancelled. Shall I cancel A? So then current density equal to N E V D. Understood or not? Is it clear? Just check once. Is it clear? Current and drift velocity. So next one, resistance and resistivity. We'll discuss about resistance and resistivity. Let's start. Discuss about resistance and resistivity. Resistance and resistivity. So I will explain one activity. So based on that one we can see. Okay. So nichrome wire, first case is length of the conductor is L, area of the cross section A. So next one, twice of the length, area of the cross section is A. Okay. Coming to third one, area of the cross section 2A, L and 2A area of the cross section. Okay, area of the cross section is 2A, length is L. Understood or not? So area of the cross section A, length 2L. And in these three cases, so I am taking nichrome wire. Yes or no? So in the three cases, I am considering the nichrome wire. Coming to the fourth case, so I am taking the copper wire. Length L, area of the cross section A, copper wire. Okay. So I hope you understood the concept. So I am taking this is A and B. So in between that you have to connect all these three cases, four cases, current. So here cell, switch, okay. Positive term, negative term, current is flowing. Now observe. So case 1, nichrome wire of length L, area of the cross section A. You have to connect between A and B. You have to connect between A and B and observe the reading of ammeter. And the second case, so length is twice. Area of the cross section is same, but length is twice. Connect between A and B and identify the observe the reading of ammeter. And in the third case, area of the cross section is twice, length is same. Length is same as we consider in the first case. Observe the reading of ammeter. And in the fourth case, so in these three cases, we used nichrome wire. Now we are using copper wire. Now observe, place this copper wire of length L and area of the cross section A. So connect between A and B and observe the reading of ammeter. Okay. By observing these four cases, okay, so we can conclude that resistance is directly proportional to length of the conductor. Here you can observe you are using same length, area of the cross section. When you are using here, so resistance increases, ammeter reading decreases. Okay, ammeter reading decreases. Understood or not? So resistance is inversely proportional to area of the cross section. Resistance is inversely proportional to area of the cross section. So R is directly proportional to L by A. R equal to rho into L by A. R equal to rho into L by A. Understood or not? So resistance is directly proportional to length of the conductor. Resistance is inversely proportional to area of the cross section. Resistance is directly proportional to L by A. R equal to rho into L by A. R equal to rho into L by A. Understood or not? So by observing these four cases, we can conclude that if resistance, so length of the wire is this much, resistance will be less. If you increase the length twice, okay, resistance increases. By that conductor, so current decreases, right? And coming to the next one, area of the cross section increased. So more current goes, right? Then resistance decreases. So R is inversely proportional to area of the cross section. And one more thing, instead of nichrome wire, I took another wire, that is copper wire. Okay. So in the place of nichrome wire, so I placed copper wire, right? Then we can conclude that okay. Yes. So I hope it is very clear. Now we can see. Now we can see. So resistance is directly proportional to length of the conductor. Resistance is inversely proportional to area of the cross section. R is directly proportional to L by A. R equal to rho into L by A. Understood or not? SI unit of resistance is ohm. Symbol. So resistance depends on length and area of the cross section. Length and area of the cross section. And coming to the next one, resistance depends on temperature. Resistance depends on temperature. Resistance depends on nature of the material. Nature of the material. Understood or not? Coming to here, rho equal to RA by L. So rho equal to ohm meter square by meter. Meter can cancel, ohm meter. So ohm meter. Understood or not? Ohm meter. Next symbol ohm meter. So resistivity depends on temperature. Resistivity depends on temperature. Next, resistivity depends on nature of the material. Nature of the material. Nature of the material. Understood or not? So just check once. Just check once. Is it correct or not? Is it correct or not? So if it is correct, do like, share and subscribe. So if the concept is clear, just let me know by clicking like button, by sharing, by subscribing. Okay, so resistance is directly proportional to L. Resistance is inversely proportional to area of the cross section. So R is R equal to rho into L by A. Okay, so these are points. And coming to the temperature, so remaining all points we discussed. Only temperature we didn't discuss. I will explain temperature now. I will explain temperature. Just check once. So I will discuss about temperature. Okay. When temperature increases, so listen carefully, observe carefully. When temperature increases, so the free electrons in the conductor increases and the motion of the free electrons increases. Motion of the free electrons increases, right? And one more point, ions of the conductor moves with greater amplitude. Ions of the conductor moves with greater amplitude. So even electrons are moving with greater amplitude. Then what happens? So at that moment, remember, observe carefully, at that moment, when ions of the conductor move with greater amplitude, at that moment, resistance and resistivity decreases, conductivity increases. At that moment, I said, at that instant time. So in the next second, so when ions are moving with greater amplitude, then collisions will take place. Yes or no? Between the ions. Yes or no? Understood or not? So collisions will take place between electrons to electrons. Then that time what happens? Resistance and resistivity increases, conductivity decreases. Resistance and resistivity increases, conductivity decreases. So by this we can conclude that when temperature increases, resistance and resistivity also increases. Understood or not? When temperature increases, resistance and resistivity also increases. Is it clear? Yes. So R is directly proportional. And one more point. Sir, if temperature increases, as you said, resistance and resistivity also increases. Very good. But what about length and area of the cross section? So those two, okay, so those two quantities also increases, right? Yes, sir. So those also will increases. But yes, those also changes, increases. But those changes are very quite small. Okay, very less. Very less. Okay, that time we are taking R is directly proportional to L, R is inversely proportional to area of the cross section, R is directly proportional to L by A, R equal to rho into L by A. R equal to rho into L by A. So L by A is constant. L by A is constant, then R is directly proportional to rho. R is directly proportional to rho. Is it clear? Yes. So alpha is the temperature coefficient of resistance. Alpha is the temperature coefficient of resistance. 1 plus alpha T minus T naught. Then all T equal to R naught. So actually R naught is the temperature T naught. RT equal to temperature T. Even rho naught is a temperature T naught. Rho T equal to a temperature T. At temperature T. So now R naught plus naught into T minus T naught equal to RT minus R naught equal to R naught alpha T minus T naught. So you are multiplying and taking these terms to here. Then alpha equal to R naught T R naught by R naught into T minus T naught. Understood or not? So this is the temperature coefficient of resistance. So now temperature coefficient of resistivity. Rho naught by rho naught into T minus T naught. Understood or not? Is it clear? Is it clear? If it is clear, just let me know by clicking thumb. So alpha equal to RT minus R naught by R naught into T minus T naught. Rho equal to, so alpha equal to rho T minus rho naught by rho naught into T minus T naught. So this is about temperature dependence of resistance and resistivity. Resistance and resistivity. Is it clear? So next one, we'll discuss about Ohm's law. So now we'll discuss about Ohm's law. Okay. So what is the meaning of, what is the definition of Ohm's law? What is the definition of Ohm's law? So Ohm's law is nothing but, so the potential difference across the ends of the given metallic conductor is directly proportional to current flowing through it at a constant temperature. The potential difference across the ends of the given metallic conductor is directly proportional to current flowing through it. Okay, so V is directly proportional to I, V equal to IR. So here I am taking this resistor. So potential difference, this is a voltmeter, current is flowing I. Okay, so here you can see V is directly proportional to I. The potential difference across the ends of the given metallic conductor is directly proportional to current flowing through it. V is directly proportional to I, V equal to IR at a constant temperature. At a constant temperature and physical conditions also same. At a constant temperature and physical conditions also same. Okay, V equal to IR. So Ohm's law gives the definition of resistance. Ohm's law gives the definition of resistance. Okay, so next. So we'll draw the graph for ohmic conductors. Ohmic conductors, ohmic conductors. So you can see this the graph. The graph is starting from origin, V on y-axis, I on x-axis, theta, slope, tan theta equal to R, tan theta equal to R. So slope of the graph, tan theta equal to R. So for ohmic conductor, the graph is straight line. For ohmic conductor, the graph is straight line. For non-ohmic conductors, the graph is curve. Non-ohmic conductors. For non-ohmic conductors, the graph is curve. So here you can see. So V on y-axis, I on x-axis, the graph is curve. Okay, so here you can observe. Here you can observe this the V1 and here is the I1. This one is V2 and here is the I2. So I am taking here this the P and Q. So here you can see V1 by A1 equal to R1, that is at P. V2 by I2 equal to R2, that is at Q, but R1 is not equal to R2. R1 is not equal to R2. So, okay, ohmic conductors are nothing but the conductors which obey Ohm's law, those are called ohmic conductors. The conductors which does not obey Ohm's law, those are called non-ohmic conductors. Non-ohmic conductors. So I hope it is very clear, right? So ohmic conductors and non-ohmic conductors. Next one we will discuss about electromotive force. Electromotive force. Okay. So let's start about electromotive force. So what is electromotive force? Electromotive force. Electromotive force. What is that? Electromotive force. Electromotive force. Normally, so this is the cell, or you can take cell. So cell is connected. So positive terminal, negative terminal, resistor, current is flowing. So normally positive charge will move from positive terminal to negative terminal. When you connect the cell to the circuit, automatically positive charge will move from positive terminal to negative terminal. So when it is reaching to the negative terminal, the positive charge, the work done to bring unit positive charge from low potential to high potential or negative terminal to positive terminal. Okay, so we are doing work. We are doing some work to bring unit positive charge from negative terminal to positive terminal or low potential to high potential. That is called electromotive force, EMF. So E equal to W by Q. V equal to W by Q. Understood or not? So that is the electromotive force, or the work done by the cell on the charge to bring from positive terminal, negative terminal to positive terminal or low potential to high potential is called EMF, electromotive force. Okay, so coming to the next one, resistors are connected in series combination. Resistors are connected in series combination. Resistors are connected in series combination. Understood or not? So I am taking resistors. So as I mentioned in the previous case, in the previous concept, resistor is a device which is used to oppose the electric current. Okay. So resistance is the phenomena of opposing the electric current in the circuit. SI unit of resistance is ohm. So here three resistors, 1, 2 and 3. Okay, so I am considering here. Now you can observe. So R1, R2, R3 across R1 V1, across R2 V2, across R3 V3. So positive terminal, negative terminal, positive, negative, current is flowing, I is flowing. So throughout the circuit, current is same. Yes or no? Throughout the circuit, current is same. Throughout the circuit, current is same. Because all resistors are connected in series combination. So series combination. So IS equal to I1 equal to I2 equal to I3 equal to I. Because so throughout the circuit, current is same. From Ohm's law, V equal to IR. From Ohm's law, V equal to IR. So Vs equal to V1 plus V2 plus V3. V potential difference across R1 V1, across R2 V2, across R3 V3. Potential difference is different. So IRS equal to IR1 plus IR2 plus I R3. So I am taking common. So if you take I common, R1 plus R2 plus R3, I get cancelled. Rs equal to R1 plus R2 plus R3. So if n number of resistors are connected in series combination, Rs equal to Nr. Rs equal to Nr. So once observe there. Once observe. So is it clear or not? So let me know. Let me know. Is it clear or not? Okay, resistors are connected in series combination. So next one we will discuss about resistors are connected in parallel combination. Resistors are connected in parallel combination. If the concept is clear, if you understood the concept, give a like, share and subscribe the channel. If you like the concept, if you understood the concept, if it is clear, the explanation is clear means, so let me know by clicking, by subscribing, by sharing. So share to your friends, ask your friends to join to the class. Next one, parallel combination. Parallel combination. So I am taking resistors are in parallel 1, 2, 3. Okay, so R1, R2, R3 across this one I am connecting potential difference V, right? So ammeter, so switch, sorry, here switch, this is a battery switch. So current is flowing, ammeter reading, voltmeter reading through R1 I1, through R1 I1, through R2 I2, through R2 I2, through R3 I3. So current is dividing. Whatever the current is coming from here, it is dividing across. So through R1 I1, through R2 I2, through R3 I3. But potential difference is same. Potential difference is same. So across R1, R2, R3. So we know Ohm's law, V equal to IR, I equal to V by R. Yes or no? So here VP equal to V1 equal to V2 equal to V3 equal to V. The physical quantity which is constant in parallel combination. The physical quantity which is constant in parallel combination is potential difference. The physical quantity which is constant in series combination is current. Okay. So yes. So now you can take IP equal to I1 plus I2 plus I3. So that is nothing but V by RP equal to V by R1 plus V by R2 plus V by R3. So now I am taking V common. 1 by RP equal to 1 by R1 plus 1 by R2 plus 1 by R3. So V will get cancelled. And then 1 by RP equal to 1 by R1 plus 1 by R2 plus 1 by R3. Is it clear? Yes. So if n number of resistors are connected in, if n number of resistors are connected in parallel combination, if n number of resistors are connected in parallel combination, that is, so 1 by Rp equal to R by N by R. N by R, then Rp equal to R by N. Okay, if n number of resistors are connected in, so R effective, R equivalent, Rp, anything we can take. So 1 by Rp equal to N by R, Rp equal to R by N. Okay, so this is about resistors are connected in parallel combination. So actually some circuit we may not reduce into simple series and parallel. Simple series and parallel. That time we will use Kirchhoff laws. We'll use Kirchhoff laws. Kirchhoff laws are nothing but, there are two laws are there. One is junction law, another one is loop law. One is junction law, another one is loop law. So coming to junction law, first one is junction law. So Kirchhoff laws. First one is junction law. Second one is loop law. So coming to the junction law, the algebraic sum of all the currents meeting at a junction equal to 0. Okay, so junction is nothing but where two or more conductors meet at one point. So here you can see, so I1, I2, I3 and I4. Sum of the currents reaching to the junction equal to sum of the currents leaving from the junction. Okay, the algebraic sum of all the currents meeting at a junction equal to 0. So now sum of the currents reaching to the junction is equal to sum of the currents leaving from the junction. Understood? Coming to loop law, there are 4 points are there. So one by one we will discuss. Point number 1. So you are going through the cell from positive terminal, from negative terminal to positive terminal, A to B. Then EMF of the cell. This is the path. So path is very important. So you are moving from negative terminal to positive terminal. Then EMF of the cell is positive. Coming to the second one, so you are moving from positive terminal to negative terminal. So positive, negative, this is the path. This is the path. So EMF of this cell is negative. So one thing you have to remember in which, so finally where you are reaching, final destination or final point is here positive, so positive EMF, here negative, so negative EMF. Only you have to think about cell. Coming to the next one, third one, resistor. So this is the current, point A and point B, you are moving along the path. This is R, this is the path. If you are moving along the current direction, the voltage drop is there, so that is negative IR. And coming to the fourth one, so you are moving across the resistor, okay, so B, A, so you are moving opposite to the current direction. So current is in this direction, this is the path. So you have to consider one path. So to move, to go, okay, so I am going in this path, so you are moving opposite to the current direction. So the IR term is positive. Okay, these points are very, very important. If you remember these points, so you can solve, you can do any circuit diagram. Okay, so I hope it is very clear. Understood? Yes, this is about Kirchhoff laws. And coming to the internal resistance and heating effect of electric current. Internal resistance, same with the help of loop law I will explain. Internal resistance, okay, so when electron is moving through electrolyte in the cell, it experiences some resistance. If automatically resistance is there, voltage drop is there. Yes or no? Voltage drop is there. When electron is moving through electrolyte in the cell, it experiences some resistance. So that is internal resistance. So I am taking the cell. This is the internal resistance R. Okay, so this is the E. From, so I am taking this the A, B. So along the, this is the current direction. You are moving the path. This is the path, along the current direction you are moving. So internal resistance R, so EMF E. So potential equal to E minus IR. Is it correct or not? So negative to positive you are moving, positive EMF, and along the current direction you are moving. So voltage drop, that is current. Okay. So IR term is negative. Yeah, next combination of cells only. After heating effect of electric current, we'll discuss about combination of cells. That is nothing but grouping of cells. So next, heating effect of electric current. After that, combination of cells. Heating effect of electric current. Heating effect of electric current. Electric current. Heating effect of electric current, V equal to W by Q. So you know work done. Work done to bring unit positive charge from one point to another point within the conductor. Okay, so that is called V equal to W by Q. From this, W equal to V into Q. So we know electrical power, rate of doing work, that is called P equal to W by T. Now VQ by T. We know Q by T is rate of flow of charge. The flow of charge with respect to time, that is current. So here P equal to V into Q by T, that is V equal to Vi, P equal to Vi. So whatever the energy is given to the conductor, okay, that will become in the form of heat. So here Vi into T, so that is Vi into T. We know V equal to IR. V equal to IR. Then substitute here, then H equal to IR into I into T, then H equal to I square RT. Heat produced in the conductor, here you can observe. So V equal to W by Q. Potential difference equal to work done to bring unit positive charge from one point to another point. W equal to VQ. So rate of doing work P equal to W by T. So W equal to VQ by T. Q by T is I. P equal to V into Q by T, Pi. Whatever the energy is given to the conductor, that will be in the form of heat. So P into T, P equal to Vi, V equal to IR, H equal to IR into I into T, H equal to I square RT. Heat produced in the conductor is directly proportional to, yes, power, that also we can write. I square R, V square by R. Yes, that also we can write. Electrical power. Okay, so heat produced in the conductor is directly proportional to square of current. Heat produced in the conductor is directly proportional to resistance. Heat produced in the conductor is directly proportional to time. Okay, so this is also known as heating effect of electric current or Joule's law of heating. Joule's law of heating. Understood or not? So next one at the final end. So grouping of cells. So by this we can conclude the today topic. So if the concept is clear, if you understand the concept, so do like, share and subscribe to Student Brand. Okay, share to your friends, ask your friends to join to the class. Okay, share to everyone as much as possible, as soon as possible. Because very important topics are going on. So +1, +2 and even for grade 10. So you can share to your juniors, seniors. So if you are in 11th, seniors. If you are in 12th, juniors. So if you are in 9th, seniors. If you are in 10th, juniors. And seniors also too. Okay. So come to the point, grouping of cells. Grouping of cells, you can see I am connecting cells in series combination. Yeah, if you are in college, you can spread your friends to everyone regarding the channel. So how we are working, how we are doing, how we are dedicating for the concepts. So one, I am taking this a resistor. So EMF, internal resistance, EMF, internal resistance, EMF, internal resistance, current is flowing. positive, negative, positive, negative, positive, negative. So this is external resistance. External resistance. Understood or not? I hope it is very clear. Now you can see E and R of each cell is same, right? Now then, net EMF when cells are connected in series. So what is total current same? So here also net EMF is E. Net EMF is E. But resistance is N. So N number of resistors are connected. You have to take R you are taking common. So it is the number, right? So then net internal resistance. Net internal resistance that is NR. Net internal resistance is NR. So total external resistance is R. External resistance is R. External resistance is capital R. Total resistance is that is NR plus capital R. Then current I equal to net EMF by net total resistance. So that is nothing but I equal to so NE, right? NE by NR plus R. NR plus R. Okay, so in parallel combination, yes, in parallel combination is E. Yeah, correct. N. Yes, that is true. NE by. So in series we'll multiply with N. So in parallel we'll get E. That is true. Correct. Net EMF NE by NR plus R. So coming to the parallel combination, same in parallel combination we'll write. So in this parallel combination we'll get a different value. Here we'll get NR different. So external resistance same only. Okay, so here you'll get E. Net EMF. So here we have to write. So remaining all things. Now we will see cells 1, 2, external resistance. So E and R of each cell is connected to one junction. All positive terminals are connected to one junction. All negative terminals are connected to another junction. So this is external resistance R. Net EMF equal to now. So in parallel combination, as we know that in parallel combination, net EMF is E. Understood or not? Net internal resistance in parallel combination. So R by N. So 1 by RP equal to we know that N by R. RP equal to R by N, right? So but here internal resistance smaller. That's why I am writing smaller. Okay, I hope it is very clear. Now external resistance same. Total resistance is R plus R by N. Now total I equal to, so net EMF E by total resistance is R plus R by N. Okay, so finally we completed. Completed. So thank you so much. So we'll see in the next class with a different topic, right? So just check once. So if the concept is clear, if you understand the concept, if the topic is clear, so let me know by doing like, share and subscribe, and inform to all your friends, share to all your friends regarding the channel. Just spread one word regarding the channel if you like the content, if you like the channel. So E R by N, R plus R by N, E by R plus R by N. Yes. So thank you so much. So do like, share and subscribe to Student the Brand. Thank you so much. We'll see you in the next class with a different topic. Okay, with a different concept. So this is Ever Siva sir signing off. Thank you.